Hello PU2 champions, your final exam is just a few days away, and at this point of time revising the whole syllabus is really difficult and time consuming. So to help you to revise the entire chemistry syllabus, I have planned 3 videos for the revision of the chemistry. The first video was on physical chemistry, which is already published, and it included all the 3 chapters, that is solutions, kinetics and electrochemistry. And the second video, which I have already published, was on inorganic chemistry, that included DNF block elements and coordination compounds. And in today's video, we are going to do the revision of the vast syllabus of organic chemistry. The entire organic chemistry, all the 5 chapters will be covered in this one single video, where I will be focusing on all the important reactions that you need to remember and other important concepts. So let's get started with the first chapter of organic chemistry, that is haloalkanes and haloarenes, which has a weightage of 9 marks in our final exam. So let's see what we have in this chapter. So first we'll talk about the nature of CX bond. Next, we'll talk about preparation of haloalkanes, preparation of haloarenes, physical properties, chemical reactions of haloalkanes and chemical reactions of haloarenes. Okay, so first if I talk about the nature of CX bond, okay, if you see C and X, okay, so X is what it is, electronegative in nature, right? So it is delta minus and carbon is delta plus. So the carbon attached here is electrophilic in nature, and any nucleophile can attack on this carbon to give you CNU bond. Okay, so that is the nature of the CX bond. Now, if I talk about the bond strength, so CF is more stronger than CCl, then CBr, and then CI. This is because of the strength between carbon and fluorine, carbon and chlorine based on their size. Now, the polarity is the root cause of the nucleophilic reactions. Okay, so we have already explained, since the X is more electronegative, the carbon is electrophilic in nature. Now, let's see the preparation of haloalkanes reaction. So, we can prepare haloalkanes from 3 important sources. The first one is our addition, so from alcohols. The second one is from hydrocarbons, and the third one is using halogen exchange method. Now from alcohols, I have from alkanes and alkenes. Next, from alkenes, I have addition of HX and addition of X2. And in halogen exchange method, we have Finkelstein reaction and Schwarz reaction. KCT 2026 examination is very close, and if you really want to ace this examination with the top rank and want to secure a seat in the top colleges of Karnataka, then only studying will not help you. You need to practice test, you need to analyze, and you need to improve. And for that, you need a perfect test series. So to help you with this, I have launched the Fighter KCT 2026 test series, which is designed by KCT experts and is based on KCT exam pattern and syllabus. Okay, here you will get detailed solutions, video solutions for chemistry, and the most important thing, a detailed analysis report after every test, which will help you to analyze your strength and weak areas. And all these things are available at a very affordable price of just rupees 399. So if you really want to boost your preparation, this test series should be there in your, I can say, resource list. So the link is there in the description section. So click on the link and purchase right now, as the prices may go higher later. Now first let's understand from alcohols. So if you take alcohols and treat it with HCl plus ZnCl2, you will get RCl plus water. If you treat it with NaBr plus H2SO4, you will get RBr plus NaHSO4 plus water. Now if you treat it with PX3, where X is equal to chlorine or bromine, then you will get Rx plus H3PO3. Next, you will get PCl5 if it produces RCl, that will give you POCl3 plus HCl. Next, we have red phosphorus plus X2. Here you can use bromine or iodine to give you Rx, and the SOCl2, the best method, that will give you RCl plus SO2 plus HCl. Okay, now here SO2 is a gaseous byproduct and HCl is also a gaseous byproduct. So both of them will evaporate and you will have only RCl. Okay, so that is why this is the most preferred method. Now we will talk about from hydrocarbons. So if I have alkanes, okay, and if you treat alkanes with chlorine and UV light or heat, then in that case what will happen, this will I can say, just a minute. So here what will happen, chlorine will be replacing the hydrogen, here there will be a replacement, so you will get a mixture of products. Okay, all the possible products are formed, and that is why this is not a preferred method. So if you say I just cannot get 1 chlorobutane here, I'll get 1 chloro as well as 2 chlorobutane, right? So that is why this method is not preferred. Now if I move to the next one, that is from alkenes, you have addition of HX. So here the Markovnikov rule is followed, which says that the negative part will go to the carbon having less number of hydrogen. Okay, less number of hydrogen. So here X minus will be there, it will attack on the carbon and you will get a product like this. Next, we have from alkenes, that is addition of X2. Here we have Br2CCl4. So the double bond will break and here Br will be added. So it is vicinal dibromide will form. On the vicinal carbons, the X groups will be attached. Now we'll talk about halogen exchange method from Finkelstein reaction. So if you have Rx plus NaI in presence of dry acetone, you will get Ri plus NaX. Now Schwarz reaction, when you have CH3Br plus AgF, you will get CH3F plus AgBr. Now here in case of metallic fluorides, you can use AgF, Hg2F2, COF2 and SbF3. Now next we'll talk about preparation of haloarenes. So there are two methods again from haloarenes, hydrocarbons and from amines. So if I talk about hydrocarbons, okay, so you can just, this is Friedel-Crafts alkylation, Friedel-Crafts reactions, sorry, not Friedel-Crafts. If you take any group like toluene or any normal benzene and you just treat it with X2 and Fe with dark, so you will get X. This CH3 group is what? It is an ortho para directing. So the X group is attached at ortho and para position. Okay. So that is how you can add. Then Sandmeyer reaction is the second one, where you take first aniline, treat it with NaNO2 and HX, you get benzene disonium chloride, and then it gets converted, or it is treated with the salt of copper Cu2X2 to give you halobenzene or aryl halide. Okay. Now you have this one treating with Ki, this will give you iodobenzene plus N2. Okay, it will give you aryl halide plus N2. Next, we have physical properties, the increase with the increase in the mass, decrease with the increase in branching. So if the mass increases, the melting point, boiling point increases, and if the branching increases, then also the melting point, boiling point decreases. Now density, as the mass increases, the density also increases. And if I talk about solubility, it is less soluble in water, more soluble in organic solvent, and solubility decreases with the increase in mass. If the R group keep on increasing, then the solubility decreases. Now we will talk about the chemical reactions of haloalkanes. The first one is your nucleophilic reactions, then we'll talk about elimination reaction, and then we'll talk about reaction with metal. Now nucleophilic reaction, here we will study three important parts. First is the type of nucleophile, mechanism of nucleophilic reactions, and the stereochemical aspects of this one. So as we saw in the starting, that CX bond is electrophilic, means the C is electrophilic in nature, so the nucleophile can easily attack on this one. Now we will see what are the different types of nucleophile which can attack on this X, on this carbon, and what product it will get. So if you treat it with OH minus, then ROH will be formed. If you treat it with H2O, then the ligand, then the nucleophile is H2O, and here also we will get ROH. If you treat it with NaOR, here the nucleophile is RO minus, and it will give you ROR, which is the ether. Now if you treat it with NaI, here the nucleophile is I minus, you will get Ri. If you treat it with NH3, then you will have the nucleophile NH3, and it will treat it with RNH2. Now similarly, if you have KCN, here the nucleophile is CN minus, and it will react to give you RCN. Okay. Next you have AgCN, and when it is reacting, you will get the nucleophile here itself is AgCN, and then it reacts to give you RNC. Now if you have KNO2, here you have ONO. Okay. Now that will react to give you RONO, and if you have AgNO2, it will be, the nucleophile here is also AgONO, and this one will react to give you RNO2. Next we have RCOO minus Ag, so we have RCOO minus, if that reacts, you will get here R-COOR. Lithium aluminum hydride, the nucleophile is H, you will get RH, and if you have just R-M, that is any Grignard reagent, here you will get RR as the product. Now we'll talk about the mechanism, SN1 mechanism and SN2 mechanism, by which the reaction takes place. So in SN1, the reaction takes place in two steps. First is the formation of carbocation. This is a slow step, and the second step is the attack of the nucleophile. Okay, so here you will get this as the product. Now we will have SN1 mechanism here in detail. So the reaction type, it is unimolecular. Okay, and it is follows first order kinetics, and here it only depends on the concentration of the alkyl halide. The steps involved, as we saw, the first one is the formation of carbocation, the second step is the attack of the nucleophile. Now solvent preference here is polar protic solvents. The carbocation stability order is 3 degree, 2 degree, 1 degree. So since in this reaction a carbocation is formed, the reactivity order is 3 degree, 2 degree, 1 degree. Then special cases, if you have allylic or benzylic halides, because here also the reaction will be faster because the carbocation formed here is resonance stabilized. Next, halide reactivity order Ri, Rbr, Rcl and Rf. Okay, so if you have same alkyl group but different halide groups are present, then you will have Ri with the fastest reactivity. If there is same halogen group and different R groups, so tertiary, secondary and primary will be the order of reactivity. Okay, now moving to the SN2 mechanism, here the reaction takes place only in one step. The nucleophile attacks from the backside, forms a transition state, and then a product is formed. Okay, so this O minus OH minus attacks on the backside, and here you get a transition state like this, and that forms a product like this. Now moving to the points of SN2 mechanism, it is a bimolecular reaction. Kinetics here is follows second order kinetics, and rate depends on both nucleophile and alkyl halide concentration. Here the steps involved, it is happens in only one single step. The transition state is formed in the middle where the carbon has 5 bonds. Okay, but this transition state is very short lived. Now all the three C carbon CH bonds lie in the same plane during the transition state. Now inversion of configuration takes place, that is Walden inversion. So if you see the in the reactant, if the leaving group or the halogen is attached on this side, on the product the nucleophile will attack on the opposite side. Okay, so that is inversion of configuration takes place. Now if there is more bulky group, the reaction will be I can say will slow down, because if bulky groups are present, the nucleophile cannot attack easily from the backside, so that is why the reaction will be slowed down. And for the second order reaction, or for the SN2 mechanism, the order of the reaction is primary, secondary and tertiary, whereas in SN1 it was tertiary, secondary and primary. Okay, now we'll talk about the stereochemical aspects. So for that you should know certain things, or certain, I can say, basic information. So what is optical activity? Optical activity is the rotation of plane polarized light. Okay, any compound which is able to rotate the plane polarized light is called as optically active compound. Now so how will you know whether a compound will be able to rotate the plane polarized light or not? So for that what you have to do, you have to take the sample, keep it in the lab, pass the plane polarized light through it and check whether it is able to rotate or not, right? But that is not possible every time. So what you have to do here, you have a condition that if there is a chiral carbon, okay, a chiral carbon means carbon with 4 different groups. Okay, so if in a molecule there is one carbon which has 4 different groups attached, then that molecule is called as chiral, and if it is chiral it will be optically active. Now what is enantiomers? So see, now suppose I found that okay, one molecule is optically active, it is chiral, having a chiral carbon, and it is optically active, so it will rotate the light in the suppose clockwise direction. Now this particular molecule will have a non-superimposable mirror image also, which will rotate the plane polarized light in anti-clockwise direction. Okay, so what are enantiomers? I can say that enantiomers are, just a minute, one second. Enantiomers are a pair of isomers, okay, a pair of isomers which are which have or which are non superimposable mirror images on each other. Non superimposable mirror images. Okay, a pair of isomers, non-superimposable mirror images, are called as enantiomers. Okay, they rotate the plane polarized light in opposite direction. Now, if I see in SN1 mechanism, what is the first step? In the first step, there is a carbocation is formed. Right here, you can see a carbocation is formed in the first step. So now, when a carbocation is formed, the molecule becomes planar. Okay, now when the molecule is planar, the nucleophile can attack from the top as well as can attack from the bottom, right? So it can attack from the top and it can attack from the bottom as well. Okay, so this OH minus, so you can see that if the OH minus is attacking from the top, it forms this particular structure, and if it forms attack at the bottom, it forms this particular structure. So both the enantiomers are formed, okay, in equal amount. So such type of mixture where you have both the enantiomers in equal proportion is called as what? Is called as, one term is there for that. Can you tell me what is it? Racemic mixture. Okay, so in SN1 what is the product we get? A racemic mixture where both the enantiomers or both enantiomers, okay, are in equal proportion, are in equal proportions, okay, where both the enantiomers are in equal proportions. Clear? Now we will talk about SN2 mechanism. In SN2 mechanism, what happens? The OH, like there is a Br on one side and the OH is on the other side. The OH will attack from the back side. Okay, so there will be a product formed like this, which, so we can say that in SN2 there is always a reverse or inversion of configuration. Okay, you cannot have both. Suppose this is plus, then this will be minus. If this is minus, this will be plus. Okay, so that is about SN2 mechanism. Now we'll go to the second chemical reaction, that is your elimination reaction. So in elimination reaction, base, like there is a, you can see this carbon which contains the X group is called as alpha, the next carbon is called as beta. So the base abstracts the hydrogen and there is a double bond formed here, and you get an alkene in the product, like the final product. So when you have 2-bromopropene, and here while forming the product, we always follow what? We follow Saytzeff rule. Now what does this Saytzeff rule says? Saytzeff rule says that more substituted alkene will be the major product. Okay, more substituted alkene is the major product. Okay, so that is there. Now if I see that if I have 2-bromopentane, okay, now this OH minus will take one Br and one H, and there is a double bond formation here. But this hydrogen is also there. It can also abstract this hydrogen and this bromine, and we can get a double bond here. So you can see there is two possibilities. Okay, but the major product will be this one, the one which is 81%, because here you can see that there is a more substituted alkene is formed. Here you have CH3 and H2 carbon groups are attached, but here you see only one side there is carbon and all others are hydrogen. Because this is more substituted, this is the major product. Now last reaction is reactions with metals. So the haloalkanes first of all reacts with magnesium and dry ether to give you Grignard reagent. The second one, it reacts with Wood's reaction, Rx plus Na gives you Rr plus NaX. Okay, so these are the two reactions under reactions with metals. Now we will talk about the chemical reactions of haloarenes. Okay, so almost similar reactions we have: nucleophilic, electrophilic, and reaction with metal. So if I first talk about nucleophilic substitution reactions, the haloarenes, okay, if I see haloarenes, okay, haloarenes are very less reactive towards a nucleophile. What is the reason for that? The first reason is that this particular group, okay, there is a resonance here, there is a partial double bond character. Now what you see is in Rx, okay, if there is an aliphatic group, the nucleophile can easily attack on R, the X will leave, and you have RNU. Okay, this bond easily breaks. But in case of haloarenes, there is a partial double bond character here due to resonance, so this bond will not break at all. Okay, if this bond will not break, then what will happen? This X group cannot be replaced with Nu group, so you will get a resonance effect. Okay, next one, that this carbon here, it is an sp3 hybridized carbon, so this one is more electronegative, it easily polarizes this bond. But in case of this one, this is an sp2 hybridized carbon which is also highly electronegative, and X is also electronegative, so there is no polarization of the bond as strong as compared to the aliphatic one. Okay, so that is why this bond breaks here and nucleophile attacks here. Okay, next, the third one is the instability of the phenyl carbocation. So when this X bond leaves, okay, and you get a structure like this, this is a positive charge here, phenyl carbocation is formed. Clear? Moving to the next one. So does that mean that there is no nucleophilic reactions at all in haloarenes? No, it is not like that. Under some conditions, high pressure and high temperature, we can do the nucleophilic substitution reactions in haloarenes. So you can see, if I just take only chlorine and if I react with NaOH in 623 Kelvin and at 300 atm and H plus, then what will happen? The Cl group will be replaced with the OH group. Now if you have NaOH at 443 Kelvin, if you just add one NO2 group, then there will be Cl group will be replaced with OH group. Okay, now if you have NaOH at 368 Kelvin and H plus, so that what will happen here, the one more, when you add two NO2 groups, the temperature decreases. Now when you add three NO2 groups, okay, the temperature decreases here and the Cl group is formed or reacting with OH group. Okay, now moving to the next one, you have the first reaction, electrophilic reaction. So with Cl2 and FeCl3, you will get Cl at ortho position and Cl at the para position. Now if you take concentrated HNO3 and H2SO4, nitration will take place, NO2 at the ortho position and NO2 at the para position. Next we have concentrated H2SO4, SO3H at the ortho position and SO3H at the para position. Okay, now if you do Friedel-Crafts alkylation, COCH3 group will be added at ortho position and at the para position. Next, CH3Cl AlCl3 Friedel-Crafts alkylation, here CH3 is added at ortho position and CH3 is added at the para position. Okay, so these are all electrophilic substitution reaction. Now talking about the reactions with metals, so you have here, like you have Woods reaction there where Rx reacted in presence of Na. Here you have Arx, okay, means aryl benzenes, or you can just take haloarenes. It reacts with Na and dry ether. So to remove this X, you will get diphenyl plus 2NaX. Now similarly for Woods Wittig reaction, you have this X group. So in Woods reaction, it is the reaction of two haloalkanes. In Wittig reaction, it is the reaction of two haloarenes. In Woods Wittig reaction, it is one haloalkane and one haloarene that will react. So you have this one in presence of Na plus Rx, that will give you this R and benzene plus NaX. Okay. Now we will move to the next chapter, that is alcohols, phenols and ethers, which has a weightage of 10 marks. So here first we will see the nomenclature, the common names of some alcohols. Then we'll talk about the structure, preparation of alcohols, preparation of phenols, physical properties, chemical reactions of alcohols, chemical reactions of phenols, commercial alcohols, and lastly we'll talk about ethers. Okay, so first let's quickly start about the nomenclature. I'll only discuss the common names here. So when you have a straight chain, it is N-propyl. When you have this this type of group, one like this structure, okay, isopropyl. Okay, next when you have all the four carbons in one chain, then it is N-butyl. Then when you have a secondary OH group, it is sec-butyl. And when you have like this structure, you have this isopropyl group, but there is four carbon, then we call it isobutyl. Okay, now when you have tert butyl alcohol, this is called tert butyl. Here tertiary group is present, and this is the structure of glycerol, this is the structure of ethylene glycol. Okay, now we'll talk about the phenol structure. So when you have CH3 and OH, it is orthocresol. CH3 and OH here metacresol. CH3 and OH here it is paracresol. Now when you have two OH groups adjacent to each other, it is catechol, and 1 and 3 OH groups, it is resorcinol. 1 and 4, it is called hydroquinone or benzene 1,4-diol. Now we have ether structure, it is dimethyl ether, and you have diethyl ether. Next we have this one and this one, okay, methoxypropane, one methoxypropane, and then you have methoxybenzene or anisole. Then we have ethoxybenzene, okay. Next we have like I can say that this is 6 carbon, this is 7 carbon, so I have phenoxyheptane. Okay, next we have 1 to 2 methoxypropane. Okay, next we have here, you can see 1 2, so this side I have more number of carbon, so this one will be the major, I can say, parent chain. So 1 2 3 4, so I can write 3 methyl butoxybenzene. Okay, next here also you can see that you have two groups actually, okay, on this side and this side. So 1 2 dimethoxyethane. Clear? Now in ether, I also want to tell you about the structure of ether. There is some symmetrical ether, okay, and mixed ether, okay, or we also tell simple and complex ether. So in this ether of both the R groups, if they are same, then it is called symmetrical ether. If there is R groups are different, R dash and R, they are two different R groups, then it is called mixed or complex ethers. Okay. Now moving to the structure of alcohol. So in alcohols, if you see, there is a sp3 hybridized oxygen. Okay. Now in this case of alcohols, there is repulsion in this lone pairs of electrons. So the bonds come closer and the angle is less than 109 degree. Okay. Now if you see in case of phenol, the angle is exactly 109 degree. But if I talk about ethers, now these R groups are very bulky groups. They repel from each other, and this particular angle becomes more than the tetrahedral angle of 109, which is equal to 111.7 degree. Okay. Now we have preparation of alcohols. So there are different methods for preparation of alcohols. The first one obviously is from the alkenes. Okay, just a minute. Yeah, the first one is from alkenes. Second one we have from carbonyl compounds, and third one is from Grignard reagent. Now from alkenes there are two methods: acid catalyzed hydration and hydroboration oxidation reaction. Now from carbonyl compounds you have reductions of aldehydes and ketones and reductions of carboxylic acids and esters. Now next we will talk about from Grignard reagent how we can prepare alcohols. So let us see first one, that is from alkenes. So if I see the first method from alkenes, if you add H plus and water, okay, here there will be addition of OH and H following Markovnikov's rule. Okay, but if you take BH3 whole 2 and H2O2 and OH minus, here there will be addition of water, that is H and OH following anti-Markovnikov's rule. Okay, now the second method was from aldehydes and ketones. Okay, so if you take aldehydes or ketones and treat it with NaBH4 or hydrogen palladium, reduce them using these reagents, then it is called as alcohol. You will get alcohols. Now the third one was from acids or esters. So here if you treat it with LiAlH4 or H2 palladium, then it will also reduce acids and esters to give you alcohols. Now the fourth one is your Grignard reagent RMGX. So if you treat this Grignard reagent with ketones or with aldehydes, okay, then you will get alcohols. But here there is one thing that you should remember: if you treat HCHO, that is formaldehyde, with Grignard reagent, okay, that will give you primary alcohol. But if you take any other aldehyde, okay, if you take any other aldehyde and treat it with RMGX, you will get secondary alcohol. And if you take I can say ketone groups, okay, and if you treat it with RMGX, you will get tertiary alcohols. Okay, so that is the reaction order. Now one more thing important here I want to show you. For propene, suppose I have taken CH3 CH double bond CH2. Okay, now I am treating it with H plus and water, that is water in acidic medium. That will give me CH3 CH CH3. Okay, and if you are treating it with BH3 whole 2, okay, and you have H2O2 and OH minus. Okay, so that will add OH at the primary position. So you have CH3 CH2 CH3 OH. Okay, now moving to the next one, preparation of phenols. So here we have again from haloarenes. The first one is from haloarenes, then we have from benzene sulfonic acid, third one is from disonium salts, fourth one is from cumins. So if you see from haloarenes, okay, the first method from haloarenes, we have already seen this reaction in the haloalkanes and haloarenes chapter. You can treat it with NaOH at a very high temperature and pressure, then you will get a sodium salt of phenoxide ion, and if you then hydrolyze it, you will get phenol here. That's the first one from haloarenes. The second one is from benzene sulfonic acid. So if you just take benzene and treat it with concentrated sulfuric acid or oleum, you will get SO3H, and then if you treat it with NaOH and H+, you will get OH here. Next, the third one is from cumene. So this is your isopropyl benzene, which is called as cumene. If you treat it with oxygen, here two oxygens will be added in this CH bond, and after that if you do hydrolysis, you will get phenol plus acetone as a byproduct. Next, fourth one is from amine. So here you take amine and just treat it with NaNO2HCl to give you what? Benzene diazonium chloride. Okay, this is your benzene diazonium chloride. Now if you treat it with warm water, N2 plus Cl minus will get converted to OH. Okay, now we'll talk about the physical properties here. Boiling point is increase in the number of the carbon atoms, and as the number of carbon atom I can say increases, the boiling point increases, and decrease in the increase in branching. So as the branching increases, the boiling point decreases. Now solubility, since alcohols are able to form hydrogen bond with water, they are very well soluble in water. But if the hydrophilic part, means the carbon part, the alkyl group increases, then the solubility decreases. Now moving to the next one, reactions of alcohol. So we can categorize this into two parts. Okay, the first one where alcohol is behaving as a nucleophile, and the second one where the alcohol is behaving as an electrophile. Okay, so how does alcohol can behave as a nucleophile? You can see that that's a lone pair on oxygen atom. This can attack on any electrophilic carbon and can behave as a nucleophile. Now when alcohols are behaving as a nucleophile, this OH bond will break. Okay, now when alcohol is behaving as a electrophile, so first of all there is protonation of alcohol, and this carbon becomes electrophilic in nature. So any nucleophile can attack on this electrophilic carbon and this bond breaks. So when the alcohol behaves as an, I can say, electrophile, in that case the CO bond is breaking. This bond, the CO bond has to break. Okay, in case of alcohols behaving as an electrophile. In case of alcohols behaving as a nucleophile, this OH bond has to break. Okay, now we'll talk about the reactions of alcohol. So first, as we have cleavage of OH bond, as the OH bond will break, we have reactions with metals, reactions of alcohols, esterification reaction, and reaction with HX. And when there is cleavage of CO bond, in that case we have reaction with PX3 dehydration reaction and oxidation reaction. So we'll see them one by one. So first of all, those reactions where there is cleavage of OH bond. So what are reactions we have in that case? Reactions with metal and esterification reaction and the acidity order. Acidity order will cover at the end. So first of all is the reaction with metal. So this behaves as an acid, right? So alcohol behaves as an acid. It will donate H plus, and there's a salt formation with hydrogen gas. So the first one is your reaction with metal. Okay. Next, the third one is what? Third one is the esterification, okay, where alcohols can react with different compounds to give you ester. The first one is alcohols can react with acids to give you esters. Alcohols can secondly react with anhydrides to give you esters. And third, it can also react with acid chlorides to give you esters. Okay. Now we'll talk about those reactions where there is cleavage of CO bond. Under that you have, see what all reactions we have. Reaction with HX, with PX3, dehydration, oxidation. Okay. So first we will cover reaction with HX. Okay. So that will give you what? Here we have a Lucas test. So if you treat it with, so what is the reagent here? HCl and ZnCl2. Okay. So when it is reacting with HX, so here there is something important. If tertiary alcohols are there, it will react immediately. Okay. If you have secondary alcohols, it will react in 5 minutes. And if you have primary alcohols, it will not react. So like this, with Lucas reagent, we can easily distinguish between the primary, secondary and tertiary alcohols. Now reaction with PX3. Okay, so when you have ROH plus PX3, here OH group gets converted to RX. Okay, so this is the second reaction, reaction with PX3. Now, what is my third reaction? The third reaction is the dehydration reaction. So, if you take alcohols and treat it with H2SO4 at 443 Kelvin, or you can even use H3PO4, there we will get dehydrated product alkenes, and the order of dehydration is 3 degree, 2 degree, and 1 degree. Now, what is important here is the product that is formed always follow our Saytzeff rule. Okay. Now this is the third reaction that we have discussed, dehydration reaction. The first one is reaction with HX. The second one is reaction with the PX3. The third one is your dehydration reaction. And fourth one we'll talk about is the oxidation reaction. Okay. So alcohols can be oxidized, if you see, with the first reagent, that is CrO3. Here primary alcohols gets converted to aldehyde. Secondary alcohol gets converted to ketones. Now the second reagent here is PCC. Here the primary alcohols with PCC gets converted to RCHO. Now there's one more important thing, that the primary alcohols on mild oxidation can get converted to aldehyde. Now this one with RCH2OH with RCOOH, okay, that is oxidation of alcohols with a strong oxidizing agent like KMnO4 or with K2Cr2O7. Okay, you can easily convert the primary alcohols to acids. Now copper at 573 Kelvin, we have RCH2OH. Copper at 573 Kelvin will give you RCOH. Then copper at 573 Kelvin with secondary alcohol will give you ketones. Copper at 573 Kelvin with tertiary alcohols will give you alkenes. Okay. Next, we have reactions of phenol. So on that, we will understand the reactions of phenol. The first one is its acidic nature. Again, that I will discuss at the end. Esterification reaction. In electrophilic substitution reaction, I have nitration and halogenation. And then we have Coles reaction, Riemann-Tiemann reaction, reaction with zinc, dust, and oxidation. Okay. So first of all, let's talk about the acidic nature. So under acidic nature, the first reaction I have is reaction with the metal. Okay. Here also, it reacts to give you salt plus H2 gas. The second reaction is the reaction with a base. Okay, it is acting as a acid. This will react with base to give you salt plus water. So these two reactions shows the acidic nature of alcohols. Second is your electrophilic substitution reaction. So with dilute HNO3, you will get ortho and para substitution separately, but with concentrated HNO3, you will get all the 2,4,6 substituted products, that is your picric acid. Now in halogenation, if you just treat it with only bromine, then you will get 2,4,6 tribromophenol. But if you treat it with bromine and CS2, you will get ortho and para bromine. Okay, so that is your first reaction. Then you have second one, that is nitration. Okay, and this one is your halogenation. Okay, now if you see the third, we have after that Kolb's reaction. So when you take phenol and treat it with NaOH, you will get O minus Na plus salt, and you treat it with CO2 and H plus, you will get OH and COOH. Okay, and this particular product which is formed is called as your salicylic acid. Okay, so now this one is what, this is the, I can say, first reaction, second, third, fourth reaction, that is Cole's reaction. Okay, the second one is esterification, about which we will discuss. Okay, so then fifth one is Reamer-Tiemann reaction. The fifth one here is my Reamer-Tiemann reaction, where you treat it with CHCl3 and aqueous NaOH, and you get a electrophile attached here, CHCl2, and then again you treat it with NaOH, so you get a intermediate product like this, and then on hydrolysis you get salicylic aldehyde. So please remember to know all the steps of Reamer-Tiemann reaction. Next, the sixth one is the reaction with zinc dust. Here you will get phenol getting converted to benzene. And then we have the reaction with sodium dichromate that converts the phenol to benzoquinone. Clear? Now we have esterification reaction. So how the normal alcohols, means aliphatic alcohols, can react with I can say carboxylic acid, acyl chlorides and anhydrides to give you esters. Similarly, phenols can also react. So phenols can first react with carboxylic acid to give you ester plus water. Phenol can then react with anhydrides to give you esters plus acids. Phenol can react with RCOCl or acyl chlorides to give you esters plus hydrogen chloride. Okay, now if you have salicylic acid with an acetic anhydride, it reacts, you can see this OH group reacts with this particular anhydride to give you an ester here. Okay, and this ester is called as aspirin, or this is, which is very important compound. So now let's talk about the acidic nature of alcohols. So if you have any electron withdrawing group, okay, acidic nature always increases, and if you have electron donating group, then the acidic nature will decrease. And if you have plus R effect and plus, like, R effect and I effect, okay, I can write like this, that the resonance effect is always more dominant than the inductive effect. Okay, and when the electron withdrawing groups are present at ortho and para position, then only they can withdraw the electrons through resonance effect. If they are present in meta position, then only inductive effect is calculated. Okay, so I'll give you an example. Suppose I have a example like this, NO2 group is present and I have phenol here, and you have OH group, and you have OCH3 group, and you have OH, and you have CH3 group. Okay, you have to arrange it in the acidity order. Now see, NO2 is an electron withdrawing group, these two are electron donating group, so obviously this one will be the highest acidic nature. Now OCH3 donates by plus R effect, CH3 donates with plus I effect. So more donation means more decrease in acidity, sorry, basicity, acidity. So when you have plus R effect, it will donate more electrons and it will decrease the acidity to the least amount. So that is why second one, this is suppose number 2, this is number 3, and here will be 3. Here, since there is plus I effect, it is a less dominating effect, it is a less predominating effect. So what happens, the CH3 group can donate the electrons but not as much as OCH3 can donate. So that is why CH3 will be considered as less harmful for the acidic nature, and that is why it will be more acidic than the methoxyphenol. Okay, now moving to the commercial alcohols, we have methanol. Here it is called as wood spirit, and how it is prepared with CO and H2 with ZnO and Cr2O3, we get CH3OH. Next, ethanol, like if you take sucrose with invertase, it gives you glucose and fructose, and glucose with zymase gives you ethanol plus carbon dioxide. Okay, now we will talk about the preparation of ether. So first of all, we have CH3, CH2OH. When you treat it with H2SO4 at 443 Kelvin, there is elimination, but if you take at 413 Kelvin, it will give you ether here. Now the mechanism is important here. CH3, CH2OH can react with H plus to give you CH3O plus H2, and then again this can react. So in this chapter, two important mechanisms are there, that is dehydration of your alcohols to alkenes and acid catalyzed hydration of alkenes to alcohols. Okay, both these mechanisms are very, very important, and we will be discussing in the important question sections as well. Okay, now we will talk about CH3 CH2O plus H2 CH2 CH3 when it is there. So this one will attack again and you will get a ether, but this mechanism is not so important from the exam point of view, but you should not miss it. Okay, next is preparation of ether. Another mechanism is Williamson ether synthesis. Here what happens, one alkoxide ion reacts with the haloalkane, and this O minus reacts with this R to give you ROR dash. Okay, so here what you have to keep in mind, that the RX which you are having, the haloalkane, that must be a primary group. Okay, moving to physical properties, the CO bond in ethers are polar and thus ethers have a net dipole moment. Next, ethers are soluble in water because oxygen of the ether can also form hydrogen bonds with water molecule. Now we'll talk about the chemical reactions of ethers. One is the cleavage of CO bond, another is the electrophilic substitution reaction. So the first one, when I have cleavage of CO bond, here it is important that when you have R1 and R2, okay, the lone pair of electrons act on the hydrogen and they form a product like this, O plus H, and after that the X minus can either attack on R1 or on R2 and can give you R1OH plus R2X. Okay, so whether this X minus will attack on R1 or R2, that depends on a lot of factors. So if the R1 and R2 both are primary or secondary, or one is primary, one is secondary, in that case the mechanism followed is SN2 mechanism. In this case, the nucleophile always attacks on the what? On the less hindered side. Okay. Now, condition for SN1 is if any one group is tertiary, then there is SN1 reaction followed, and the X minus will attack on the tertiary one or the resonance stabilized size. So here are some examples. You can see HI is there. Now this side it is primary, this side it is tertiary. So SN1 reaction will be followed and the I minus will attack on this one. So I will get CH3OH plus Me3Ci. Okay, now if you see whenever there is a phenyl group, okay, always the bond will break here because this bond is having resonance and it cannot break easily. So the bond will break here and you will get the first product as phenol and the next product as CH3I. Okay, now if I talk about cyclohexyl OCH3. Okay, now here what will happen, you can see this side it is secondary, this side it is primary, so reaction will follow by SN2 mechanism, and that means the I minus will attack on the less hindered side, so I will attack on this side and you will get the product cyclohexanol plus CH3I. Okay, so that is how we can discuss the cleavage of ethers. So next is the electrophilic substitution reaction. So the first one, OCH3 is an electron donating group. So it will direct orthopara, it will direct the substituents to the orthopara group. So for halogenation, you can treat it with bromine CH3COH. So you will get ortho and para substituted bromo anisole. Next, if you have RCOCl, this is Friedel-Crafts acylation. So OCOR will be added at the ortho and para position. Next, we have Friedel-Crafts alkylation. Here R group and here R group will be attached at the ortho and para position. Next, concentrated nitric acid, if you take NO2 will be attached at the ortho and para positions. Okay. So this is all about the reactions of alcohols, phenols and ethers. Now we will talk about the next chapter, that is our aldehydes, ketones and carboxylic acid, which is the highest weightage chapter of 12 marks. Okay, so first we'll talk about nomenclature, structure, preparations of aldehydes and ketones, physical properties, chemical properties, carboxylic acid nomenclature, preparation and its chemical properties. So nomenclature is very common here. For aldehydes the name will end with Al, and for ketones the name will end with ONE. Okay, so this is common name is acetaldehyde, common name is benzaldehyde. Now the carbon which contains the CHO group is called as alpha, this is beta, this is gamma. So here it is beta bromo 1 2 3 4 butyl aldehyde. Next, this is called as acetone, this is acetophenone, this is propiophenone and this is benzophenone. Now we are mostly focusing here on the common names, so because other names you can easily write down. So this is formaldehyde, this is acetaldehyde. Here you can see that I have carbon like this, CH3, C and then CHO. Okay, so this is isopropyl, you have isobutyl aldehyde, sorry, you have isobutyl aldehyde. So these are the common names that you should prepare. Now, what is the structure of aldehydes and ketones? So it is a sp2 hybridized carbon, and this sp2 hybridized carbon, I can say that it is a planar structure, and the bond angle here is 120 degree. Okay. Now we'll talk about the preparation of aldehydes and ketones. So there are actually three ways how we are going to study it. Those methods which can be used for the preparation of both aldehydes and ketones. So there we have oxidation of alcohol, dehydration of alcohol, and hydrocarbons. And trust me, all these methods we have already gone through in our alcohols chapter. Okay. Next, we'll talk about those reactions where there is only preparation of aldehydes. So that includes from acyl chlorides, from nitriles and esters, and from our hydrocarbons. The third one are those reactions where there is only preparation of ketones. So from acyl chlorides, from nitriles, and from substituted benzene. So first, if I see so further there is classification of that, but we'll go that in one by one. So when now we are talking about those reactions by which we can prepare both aldehydes and ketones. So the first one in that is the oxidation of alcohol, dehydration of alcohol, and from hydrocarbons. And from hydrocarbons we have ozonolysis and hydration of alkynes. Okay. So next we will see here, just a minute. Okay, so first we will see here the preparation of both aldehydes and ketones. So if you take alcohols, okay, primary and secondary alcohol, and if you just treat it with PCC or CrO3, then you will get aldehydes and ketones. So primary alcohols will give you aldehydes, whereas the secondary alcohols will give you ketones. Clear? Now we will talk about this is the first method, that is oxidation. The second one was what? The second one was dehydration. Okay, so when you have primary alcohols and secondary alcohols and you treat it with copper at 573 Kelvin, the primary alcohols gets converted to aldehydes and the secondary alcohols gets converted to ketones. Now the third one is from hydrocarbons. Okay, the third one is from hydrocarbons. Okay, now alkenes here will be treated with O3 and ZnH2, so the bond will break here, oxygen will be added, and then you will get either aldehydes or ketones. Now the fourth one is from alkynes here. The fourth one is from alkynes. Okay, so first of all, when you add here H and OH under mercury, so following Markovnikov's rule, H and OH is added. So what will happen? You will have a structure like this. Here H, and here OH will be added. After that, what will happen? There is a what we can say tautomerization. So this bond will come here and this bond will move here, and you will get the ketones as the major product. Okay. Now we'll talk about those methods by which only aldehydes can be prepared. So first one we have is from acyl chlorides. Then we have from nitriles and esters. Here we have Stephan reaction and dival H. Then from hydrocarbons, the first one is oxidation of methyl benzene, chlorination of side chain, and Gattermann-Koch reaction. So the first one is from acyl chlorides. So if you have the first one from acyl chlorides, okay, so if you take acyl chlorides and treat it with H2 palladium barium sulfate, this chlorine gets converted to hydrogen, and this reaction is called as Rosenmond reaction. Okay, Rosenmond reaction. Now coming to the second one we have is, one second, the second one is from nitriles and esters. The second one is from nitriles. Okay, now if you treat it with nitriles and treat it with SnCl2 and HCl, so first of all it gets converted to imines, and then on hydrolysis you get RCHO. Next, the from nitriles you can also treat it with dibal H and you get RCHO. Okay, there is two things that can be done. Clear? Now the third one is from esters. You can see the third one is from nitriles and esters, right? So this is also coming under second one only. So from nitriles you have two reagents. You can either use SnCl to HCl and then treat it with H3O plus, that is one reaction, and other one is if you treat it with aluminium hydride or diisobutyl aluminium hydride or dibal H, that also will directly convert RCN or nitriles to aldehydes. If you have taken esters, then from esters also if you treat it with dibal H and water, then that will also get converted to aldehydes. Okay, so that is all about reactions with nitriles and esters. Okay, now we will talk about the third one, that is from methyl benzenes. Now if you take methyl benzene, you are treating with CrO2, Cl2 and CS2, then that will form a complex here, and that complex on hydrolysis will give you RCHO. Now this reaction is called as Itard reaction. Okay, now if you have methyl benzene, you have CrO3, and when you treat it with acetic anhydride, you get a compound. If you get a complex like this, which on hydrolysis will give you RCHO. Okay, so that is the third reaction. Next one is our Gatterman-Koch reaction. Gatterman Koch reaction. So when you have benzene and treat it with COHCl, anhydrous AlCl3 and copper chloride, here you will get RCHO. Next, the fifth one is your side chain chlorination. Side chain chlorination. Okay, so when you have CH3, you take treat it with Cl2 and H nu, and the hydrogens are replaced with Cl and then you treat it with H2 at 373 Kelvin. So OH you will get, and then on dehydration you will get RCHO. This is how we can prepare only aldehydes. Now if I talk about the preparation of only ketones, so here we have from acyl chlorides, from nitriles, and from substituted benzene. So from acyl chlorides, if you treat it with R2CD, that is dialkyl cadmium, then this Cl group is replaced with R. Okay, that is the first method, that is from acyl chlorides. The second method is from nitriles. So if you take nitriles and treat it with Grignard reagent, so you can see here it is plus, it is minus, and here it is minus, and here it is plus. So the minus one will attack here and the plus one will attack here, and once this is formed on hydrolysis, you will get the ketone. Okay, that is the second method from nitriles. And what is the third method? That is Friedel-Crafts acylation. You can just treat it with RCOCH3 and AlCl3. You will get R-COR. Okay. Now we'll talk about the physical properties of aldehydes and ketones. So the boiling point order, if you see, alcohols are having the highest boiling point because of strong intermolecular hydrogen bonding. Then you have aldehydes and ketones, and then comes ether. Now solubility, the lower members of aldehydes and ketones like methanol, ethanol are miscible in water in all proportions because they are able to form hydrogen bond to some extent. But however, the solubility of aldehydes and ketones decreases on increasing the length of the chain. When the hydrocarbon group increases, the solubility decreases. Now all aldehydes and ketones are fairly soluble in organic solvents. Okay, now we'll talk about the chemical reactions of aldehydes and ketones. So that is a bit lengthy part but important definitely. So the first category of reaction is nucleophilic addition. There we'll study about addition of HCN, addition of NaHSO3, addition of Grignard reagent, addition of alcohols, addition of ammonia and its derivatives. Next we have reduction, so where we'll talk about reductions to alcohols and reductions to hydrocarbons. Then we have oxidation. Here we'll talk about Tollens test, Felling's test and oxidation of methyl ketones. Now reactions due to alpha hydrogen, here we have aldol condensation and cross aldol condensation. In other reactions we have Cannizzaro reaction and electrophilic substitution reaction. So let us start with the first reaction, that is nucleophilic addition reaction. So if you see that, first let us understand the structure of the carbonyl group. Okay, this is the structure of the carbonyl group, and we have discussed that this is a planar molecule. So what happens now, this is delta minus and this is delta plus. So the nucleophile can easily attack on this carbon. Okay, so that is how we can get nucleophilic addition reaction. So what are different addition takes place? Addition of HCN, addition of NaHSO3, addition of Grignard reagent, addition of alcohols and addition of ammonia and its derivatives. So the first one is the addition of HCN. So what happens here, this is H plus and this is Cn minus. So the Cn minus can go here, that is attack on the electrophilic carbon, and here what you will happen, OH and Cn will be formed, and this is called as cyanohydrine. Okay, next is addition of NaHSO3. So you have Na plus and HSO3 minus. So this C is delta plus, right? So here HSO3 will add and here ONA will add. Then there is proton transfer and we get OH and OSO2Na. Now that is the, so I'll just so this is the first addition, this is the second addition. Now the third one is the addition of Grignard reagent. Here you can see this is Mg plus, this is R minus. So R minus will attack on the carbon and MgX will attach an oxygen, and then on hydrolysis you will get your alcohol. Okay, next fourth one is the addition of alcohol. So here you can see RO, how I can say this is plus and this is minus, right? So this is RO minus and this is H plus. So first of all, what will happen? The O minus will attack on C. So you will get OR dash and OH. Again, when you treat it with ROH, so this OH also will get converted to OR dash. Now this is called as hemiacetal. This structure is called as hemiacetal and this structure is called as acetal. Okay. Now we will talk about the addition of ammonia and its derivative, the fifth one. Okay, so here what happens, when you treat it with any ammonia and its derivative. So ammonia structure is NH3. If this H is there, then it is ammonia. If you replace this H with different groups, then it is called derivatives of ammonia. So what basically happens is, you just need to remember this one. When you are reacting with aldehydes or ketones, there is a dehydration. Okay, this H2O groups is leaving out and you have the product like this, that is NH. Clear? So now we will see the different derivatives of ammonia. So if Z is equal to H, then it is simple ammonia, and the product formed here like this is your imine. Now if this Z equal to R, okay, then it is called amine group, and the product formed here, it is called as substituted imine. Now if this is the Z equal to OH, then we call it as hydroxylamine, and the product formed here is oxide. Now here if this Z group is equal to NH2, then we called it as hydrazine, and the product formed is hydrazone. Next, if this Z group is equal to NH and then there is a benzene ring, then it is called as phenylhydrazine, and the product formed is phenylhydrazone. Now, if you have NO2 group, so it is 2,4-DNP hydrazine, 2,4-dinitrophenylhydrazine, which is called as 2,4-dinitrophenylhydrazone now. Now, if you have NHCO, NH2 semi-carbazide, then the product formed here is semi-carbazone. Now we have reduction reactions, reductions to alcohols and reductions to hydrocarbons, and in reductions to hydrocarbons you have Wolff-Kissner and Clemmensen reduction. So if you just treat it with LiAlH4 or NaBH4, you can reduce it to alcohols, but if you treat it with ZnHg and HCl, this is reductions to I can say alkanes, and this reaction is called as Clemmensen reduction. Okay, now similarly if you have NH2 and you treat it with ethylene glycol, then this particular reaction is your Wolff-Kissner reduction. Okay, now we will talk about the oxidation reactions here: Tollens test, Fellings test, and oxidation of methyl ketones. So aldehydes can easily react with Tollens reagents to get oxidized to the salt of carboxylic acid, and here a silver precipitate is formed, which as a silver mirror in the test tube, and it is used as a test for aldehydes. Next, in Fellings reaction, you take with copper 2+ and alkaline medium to give you again the to give you the salt of carboxylic acid, and copper oxide as a red precipitate, and this is also a test for aldehydes. But here you remember, in Fellings test, okay, in Fellings test only the aliphatic aldehyde will react, aromatic aldehyde will not react. Okay, so that is why if you want to differentiate between aliphatic and aromatic aldehyde, then you can use Swelling test. If you want to distinguish between aldehydes and ketones, then you can use Tollens test. Okay, now if you oxidize RCOH under it will give you acids. Okay, now methyl ketone oxidation is very important. Whenever you have this particular group CH3CO group and you treat it with NaOX, in that case what happens, this particular this carbon breaks and it forms CHX3 product, and this RCOO minus and Na plus is formed as the major product here. Okay, now we'll talk about reactions due to alpha hydrogen. So aldol condensation. So for aldol condensation, you need to have an alpha hydrogen, and the reagent used is dilute NaOH. So first of all, what happens in the reactant, that the alpha hydrogen is extracted and a nucleophile is produced, then it attacks on the another aldehyde to give you I can say, suppose this is CHO alpha beta. Okay, so to give you beta hydroxy aldehydes or beta hydroxy ketones. Now after that, it undergoes condensation to give you alpha beta hydroxy unsaturated compounds. Okay, now please remember, whatever examples are given in the book, you need to prepare at least those examples thoroughly. Now cross aldol condensation is similar to aldol condensation, but when you have two different aldehyde groups or one aldehyde or one ketone or two different ketone groups and you get a mixture of products, it is called as cross aldol condensation. Now here I want to tell you a trick how to find the product of this one. So suppose I am reacting with CH3CHO, okay, plus CH3CH2CHO. Okay, now suppose this is A and this is B. So when A and A will react, you will get one particular product. So for that I can write CH3COH and CH3COH. So first what you have to do, you have to connect the alpha carbon to the carbonyl carbon. Okay, and then you have to reduce one hydrogen here and you have to form this OH group here, and then just remove this OH and make a double bond here. So I'll tell you once again, because I think I'll tell you directly what you can do is, you have to just write 2 times this A group, one above other. Okay, so CH3COH and then you have CH3COH. So what you have to do, you have to connect the alpha carbon to the carbonyl carbon with a double bond. So that will give you CH3, CH, double bond, CH, COH. Okay, now if you are reacting B, that is CH3, CH2O, CH3, CH2, COH, and I'm treating CH3, CH2, COH. So in that case, what will happen? Again, you have to connect the alpha carbon to the carbonyl carbon. So that will give you what? CH3, CH2, CH, double bond C. Here it is CH, okay, but here there is another CH3 is attached, okay, and here we have COH. So like this you have to see. Okay, now when A and B is reacting, so what I will write, A and B means I'm writing A above CH3COH and B I'm writing below CH3CH2COH. So again what will happen, the alpha and the carbonyl carbon, there will be a double bond here, so you can write the product like this, CH3CH double bond C, CH3, and you have COH. That is one thing. And when you have the opposite one, means this one is reacting with this one, CH3, CH2, COH, and you have CH3, COH. Now here what will happen, again a double bond will form here, so that will give me CH3, CH2, CH, double bond CH, COH. Okay, so like this you can write the product. So this was just a trick, you can follow it to get the products quickly. Now in Cannizzaro reaction, what happens? In Cannizzaro reaction, the condition is that there should not be any alpha hydrogen and the reagent uses concentrated NaOH or KOH. So here the reactant undergoes disproportionation reaction, it gets oxidized, it gets reduced. So the aldehydes gets oxidized to give you acids and gets reduced to give you alcohols. Okay, so you can see formaldehyde will react to give you methanol, that is reduced product, and salt of formic acid to give you the oxidized product. Now if you have benzaldehyde, it gets reduced to give you benzyl alcohol and gets oxidized to give you sodium benzoate. Clear? Now in electrophilic substitution reaction, CHO group is electron withdrawing group, meta directing group. So if you do any nitration or anything, the group will be attached at the meta position. Okay, now we'll move to carboxylic acid. Here also the common names are very important, so I'm not just going for common names. So if you have two CH groups, then it is called oxalic acid. Two CH2, there's one CH2 group in between, then it is called malonic acid. Then you have two CH2 groups in between, then it is succinic acid. Three CH2 groups, then it is glutaric acid, and four CH2 group, then it is called adipic acid. Okay, and here if there are two, then we use the word dioic acid in the IUPAC nomenclature. Now there is this type of structure is called as normal benzoic acid, and if you have acid in the second carbon, then it is 2-phenyl ethanoic acid. Here when you have two COH groups adjacent to each other, the common name of this compound is called phthalic acid, and it is benzene 1,2-dicarboxylic acid. Now structure, as we have seen in the carbonyl compounds also, here also it is a planar structure and the bond angle is 120 degree. But if I compare the carbonyl carbon and the carboxylic acid carbon, okay, so if I have carbonyl carbon means of aldehydes and of acids, okay, if I compare their electrophilicity, then this carbon or the carbon of aldehydes and ketones is more electrophilic in nature than that of the acids. That is because of the, I can say, the resonance that is present in these oxygen. Okay, now, how do we prepare carboxylic acids? So we have different methods here. The first one is from aldehydes, from primary alcohols and aldehydes. So by oxidation, primary alcohols, if you oxidize with a strong oxidizing agent, you can easily get carboxylic acid. Next, from alkyl benzenes, here also we have to oxidize it. From nitriles and amides, if you hydrolyze them, you will easily get carboxylic acid. From Grignard reagent, if you treat it with carbon dioxide, then you will get carboxylic acid. From acyl halides and anhydride, so if you hydrolyze them, you will get acids. Then from esters also you have to hydrolyze them. So for the first one, if you see, the first reaction is from alcohols, right? So I have the first method here. So from, if you take primary alcohols and treat it with a strong oxidizing agent like alkaline KMnO4 or H3O plus or CrO3 H2SO4, then it will get converted to acids. The second one we have is from methyl benzenes. Okay, here also if you oxidize it with strong oxidizing agent like KMNO4, KOH and H3O plus, then the CH3 group will get converted to COOH group. Next, the third one is from nitriles. If you treat nitriles and just hydrolyze it, first it gets converted to, I can say, amides, then from that it gets converted to acids. Next, we have the fourth one is from Grignard reagent. So if I have Grignard reagent and treat it with carbon dioxide, first you get RCOOMgX, and then hydrolysis you get carboxylic acids. Next, the fifth one we have is from acyl halides and from anhydride. So if you have acyl halides and if you just hydrolyze them, you will get acids. Similarly, from esters, if you just hydrolyze them, you will get acid. And if you have esters like this also, it can give you, so whenever you have esters, okay, esters, anhydrides, acid halides, these all will give you carboxylic acid on hydrolysis. Okay. Next, we have physical properties. So their boiling point is very high because of strong intermolecular hydrogen bonding, and they also associate when they are dissolving in the solvent. And solubility is more, but when the carbon group increases, the solubility decreases. Now we will talk about the reactions. So the reactions of carboxylic acid can be divided into three parts. The first one is the cleavage of OH bond. Those reactions where there is, so if I just draw, this is my COOH group. Okay, so first category of those reactions where this OH bond will break. The second one is where the CO bond will break. The third one is where the COOH group is involved, and I have one more thing where this R group is involved. Okay, so four categories of reaction. So if I first talk about those reactions where this OH bond is cleaving, there we have just the acidic nature, reactions with metals, and the anhydride. Okay, so these two reactions are there, acidic nature and reactions with alkalis and metals. Next, for anhydride formation, where the CO bond will break, so there is anhydride formation, esterification reaction, and reaction with PCl5, PCl3 and SOCl2. Now talking about those reactions, here also we have reaction with ammonia. Now talking about those reactions where the entire COOH is involved, there we have reduction reaction and decarboxylation reaction. Now the reaction where the R group is involved, there we have the halogenation reaction and the substitution reaction. So first let's talk about those reactions where the OH bond cleavage is involved. So if you have COOH and this bond will break, if you treat it with Na, you will get a salt plus H2. And if you treat it with NaOH, you will get salt plus water. If you treat it with NaHCO3, you will get salt plus CO2 plus H2O. Now talking about the second one, that is in acidic nature, electron withdrawing group will always increase the acidity of the compound. Now talking about those reactions where there is a cleavage of CO bond. So the first one here is anhydride formation, esterification, reaction with PCl5, PCl3, SOCl2 and reaction with ammonia. So the first one you can see anhydride formation. Okay, you have one acid here and one acid here. So in this what will happen, from one of the compound OH bond will break and from another H bond will break, and then there is a dehydration. This reaction can take place in presence of P2O5. The second one is the esterification reaction. Here also the OH bond will break from here and H bond will break here, and you will get RCOOR dash plus H2O. Now reaction with PCl5, this OH group will be converted to Cl. Then here also OH group will be converted to Cl. With SOCl2 also OH group will be converted to Cl. The byproducts are important to remember. Okay. Now we will talk about those reactions where the entire COOH group is, okay, it's the reaction with ammonia is left here. So again here what will happen, this OH bond will break and from here only H will come out. So you have CONH2, that is your amide group. Now if you treat benzene with NH3, you will get first this salt and then on heating you will get CONH2, which is benzamide. Next reaction involving the whole COH group, here we have decarboxylation and reduction reaction. So if you take RCOOH and treat it with LiAlH4 or B2H6, then you will get RCH2OH, reduction of the COOH group to CH2OH group. Now decarboxylation reaction, you can treat NaOH and CO. This reaction or reagent is called as soda lime, and in that case what will happen, this COO group will be removed and you will get RH. Okay, now there's one more reaction. Alkali metal salts of carboxylic acid undergoes decarboxylation even on electrolysis. Okay, if you take this and do electrolysis, there also you will get decarboxylation reaction and form hydrocarbons having twice the number of carbon atoms present in the alkyl group, and this reaction is known as Cole's electrolysis. So if I take this one and do electrolysis, then the product formed will be RR. Clear? Now those reactions where the hydrocarbon group is involved, here the most important reaction is your HVZ reaction. You might have heard this. Haloalkanes reaction, most important reaction in this whole chapter. So if you take RCOOH and just treat it with X2 and red phosphorus, so the alpha hydrogen present gets replaced with the halogen atom. Okay, so here X is formed like this. Now in ring substitution, what happens? COOH group is a electron withdrawing group. Okay, in that case nitration will take place at the meta position and bromination will also take place at the meta position, electron withdrawing group, that's why. So now let's start with the next chapter, that is amines, which has a weightage of 7 marks in our final board exam. So we'll talk about its structure, classification, nomenclature, preparation, physical properties, chemical reactions. Then we'll talk about a very important compound, that is diazonium salt, its physical properties, chemical reactions, and the uses of amines. So first let's talk about the structure of amines. So in ammonia, it is the nitrogen is sp3 hybridized. Okay, it has 4 sp3 hybrid orbital in which the 3 orbitals are forming bond with hydrogen or with carbon, and one orbital carries the lone pair of electrons, and the geometry is tetrahedral, shape is pyramidal here, and the lone pair occupies one of the position. Due to the lone pair and bond pair repulsion, the angle is slightly less than the tetrahedral angle of 109.5 degree. Okay, now example, here we have trimethylamine, bond angle is 108 degree, and the reason being the repulsion between the bond pair and lone pair of electrons. If I see the structure, you can see this is how the structure looks. So you have N and then 3 hydrogen NH3, and here it is the pyramidal shape. Now, if I talk about the classification, we have primary, secondary, and tertiary amines. So in nitrogen, if all the 3 hydrogens are there, then we call it ammonia. If one of the hydrogen is replaced with R group, then we call this primary amine. If both the hydrogens are replaced with R group, then we call it secondary amines. And if all the 3 hydrogens are replaced with R group, then we call it as tertiary amines. Now here we have something called as simple and mixed amines. So if all the R groups are same, then it is called simple amines. And if the R groups are different, then it is called mixed amines. Now the nomenclature is very important. Again, also here we will focus more on the common names. So here you can see the 3 carbon are in one chain, so N-propyl amine. Here we have this isopropyl group, so isopropyl amine. Here you can see this is a secondary amine, so you have to write N-methyl ethanamine. Okay, you can write N-methyl ethanamine is the IUPAC name, and the common name will be ethyl methyl amine. Now here also you can see this is a tertiary amine, so you have N-dimethyl methanamine, or you can write trimethyl amine. Now here you have two sides ethyl groups and one side I have butane group. So you have N-diethyl butanamine, or you can write down diethyl butanamine. Okay, N-diethyl butanamine. Now this is the nomenclature, and here for the aromatic amines NH2, the common name is aniline and the IUPAC name is benzenamine. Here if you have CH3 group at the ortho position, this is called orthotoluidine, and bromine group at the para position, then parabromoaniline. Then you have CH3 group attached to the nitrogen, then N-dimethyl aniline. Okay, now we'll talk about the preparation of amine. So there are different methods. The first one is reduction of nitro compounds. Then we have reduction of alkyl halides, ammonolysis of alkyl halides, reductions of nitriles, reduction of amides, Gabriel thalamide synthesis, and Hoffman bromamide degradation reaction. So first of all, if I talk about the reduction of nitro compounds, okay, reduction of nitro compounds. If you take nitro compounds and treat it with SnHCl or FeHCl or hydrogen palladium, then you get RNH2. Now this reaction is called as what? This reaction is called as Stephan reduction. Okay, Stephan reduction. Now next one we have a monolysis of haloalkane. So if you take NH3 and treat it with RX, so what will happen? This X will be replaced with NH2 group. So you will get RNH3 plus X minus. And again, if you treat it with NaOH, then you will get RNH2. Okay, so this is the second one, that is ammonolysis. Ammonolysis. Next we have, once we got RNH2, again if you treat it with Rx, one of the H will be replaced, so you will get R2NH. One more R is replaced, then you will get R3N. One more N is, like, after that if you treat it with Rx, you will get a quaternary salt here. Now coming to the third one is the reduction of nitrile compounds. Okay, so reduction of nitriles. So here if you treat RCN with H2 nickel or lithium aluminium hydride, you will get RNH2, means RCH2NH2. You can also treat it with sodium and ethanol. Now this one, the fourth reaction, is the reduction of amide group. So amide group, if you treat it with lithium aluminium hydride, you will get RCH2NH2. Now the fifth reaction is very important, which is your Hofmann bromamide degradation reaction. So when this one is treated with Br2 and NaOH, this CO group is removed. Means you get one amine, one carbon less than that of the amide group. So that gives you RNH2. So if I give you an example here, so if you have RC triple bond, or let me take like CH3C triple bond N, okay, and you have CH3 CONH2, okay, just a minute. So there's no example for nitrile, is not relevant here. So if I have CH3CONH2, okay, and if I treat it with lithium aluminium hydride, and if I treat it with bromine and NaOH, okay, bromine and NaOH. So what will happen? This lithium aluminium hydride, that will convert to CH3 CH2 NH2. Okay, now in bromine NaOH, this CO group will be not there, it will be eliminated, and you will get CH3NH2. Okay, now let's talk about Gabriel thalamide synthesis. So when you have this thalamide, you treat it with KOH, so there will be N minus and K plus. Okay, and after that if you treat it with haloalkane, so you will get N minus will react with R, so you will get NR here. And after that if you do hydrolysis, this one will get, I can say it will break to give you COO minus Na plus, COO minus Na plus, and then here the product formed will be RNH2. Now we will have the physical properties, talking about physical state and order. So lower aliphatic amines are gases here, and they have a fishy smell. Okay. Now primary amines with 3 or more carbons are generally liquid, and higher aliphatic amines are solid in nature due to the strong intermolecular hydrogen bonding. Color of the aryl amines, if you see, the aniline and other aryl amines are usually colorless, but they become colored on storage due to oxidation. Solubility of amines, they are highly soluble in water due to their ability to form hydrogen bond, but as the R group increases, the solubility decreases. Next we have a comparison of solubility of amines and alcohols. So if you see, the electronegativity of nitrogen is 3, whereas of oxygen is 3.5. So alcohols are more polar than amines, and alcohols can form stronger hydrogen bonding than amines. So definitely alcohols are more soluble than amines. Now example, suppose butane 1 oil and butane 1 amine is there, which is more soluble in water. Obviously butane 1 oil will be more soluble because of higher electronegativity of oxygen. Now solubility in organic solvents, we have alcohols, ethers and benzene. In all these, amines are very easily soluble. Now intermolecular hydrogen bonding in amines, if you see, primary amines show the highest intermolecular hydrogen bonding because they have more H, then secondary amines, and then tertiary amines. So the order is primary, secondary and then tertiary. Next, the boiling point will depend on the intermolecular hydrogen bonding. Since primary amines have stronger hydrogen bonding, so there the boiling point is more. So the order of the boiling point is primary, secondary and tertiary. Now if I see the chemical reactions of amines, so first we'll talk about the basic nature of amines, then alkylation, acylation, carbylamine reaction, reaction with nitric acid, then you have reaction with aryl sulfonyl chloride, electrophilic substitution reaction. In that we have nitration, sulfonation and halogenation. So if you talk about the basic nature, in gaseous phase, the order of the basicity is tertiary, 3 degree, 2 degree, 1 degree and NH3. But when we talk about in aqueous medium, the order gets different because there are so many factors which affect the basicity. Here the main factor is plus I effect. Okay, but in aqueous phase, the factors that are affecting is plus I effect, then you have solvation effect. After solvation effect, you also have that is steric hindrance. Okay, and all these factors contribute to give you an order like this. So if the R group is ethyl group, then we have 2 degree, 1 2 degree, 3 degree, 1 degree and then ammonia. And if the R group is a methyl group, then the order is 2 degree, 1 degree, and 3 degree, and then ammonia. This is because there are a lot of factors affecting the basicity inside the aqueous phase. Now, aryl amines and ammonia, if I consider, ammonia are definitely more basic, because in aryl amines, what happens, if you see the structure, here we have this NH2 group, okay, and in NH2 group, the lone pairs of electrons are there, which is under resonance, right? So these electrons are under resonance, and as a result of which the aryl amines are less basic, they are not available for donation. Now, if I talk about the reactions, chemical reactions of benzene disonium chloride, sorry, of the ammonia. So the first reaction we have seen is, let us go back, basic nature we have discussed, alkylation, okay. So if you see alkylation, when I treat R NH2 with Rx, so what will happen, this hydrogen will be replaced with R, so you will get R2NH, okay. So this is the first one, which is called as your alkylation reaction. Okay, this is second one, sorry, first one we have already discussed the basic nature, then we have alkylation. Then the third one here is your acylation. Okay, in acylation, what happens, you have NH group is there, it reacts with this CO group, and you get RNHCOR. Okay, so this is I can say amide group, but a substituted amide is formed, so that is in the acylation. Now for acylation, it can also react not only with acyl chlorides but also with anhydrides. Okay, so if it also reacts with anhydrides, so here also you will get the same acylated product. And if you have benzene group here, then the same reaction can be also called as benzoylation, just because we have here benzoyl chloride. Okay, so this comes all under addition of acyl group. Now the fourth reaction is what, reaction with we call it as carbyl amine reaction. Okay, so in carbyl amine reaction, what happens, RNH2 reacts with CHCl3 and KOH. With heating, you get RNC, which is an isocyanide, and this isocyanide, okay, due to this isocyanate, what happens, it gives a foul smell. Okay, now because of this foul smell, we can easily distinguish the amines. So I can say that the reaction is due, means this reaction is a test for primary amines. Okay, secondary and tertiary will not react here. Now the third one is reaction with nitrous acid. So when you have aliphatic amines, okay, if it is aliphatic amines with HNO2, you will get ROH. Okay, this is the fifth reaction. Alcohols, but if it is an aromatic amines with HNO2, you will get benzene disonium chloride. Okay, so I think we have discussed reaction with nitric acid. Now we'll talk about reaction with aryl sulfonyl chloride. Okay, now this aryl sulfonyl chloride is called as Hinsberg reagent. Okay, please remember Hinsberg reagent, and the main use of this reagent is to distinguish between primary, secondary, and tertiary amines. So when you have this benzene sulfonyl chloride and you are reacting it with a primary amine, so here HCl will be removed and you will get a salt like this. And this salt, because this has an acidic hydrogen, it is soluble in alkali. Okay, soluble in alkali. Now if you see, we have the secondary amine, so here HNCl will react and you will get a compound like this, and this one is a salt, and in this salt there is no hydrogen in N, so that will require what, it is insoluble in alkali. Insoluble in alkali. Okay, now if you have all the three R groups, all the three H is replaced with R groups, then here what will happen, there will be no reaction, and that will give you a tertiary amine. So how will you distinguish? If it is a primary amine, the salt which is formed here is soluble in alkali, and the second one, the secondary amine which is formed, that one is salt is formed but it is insoluble in alkali, and the third one, when it is formed, that is also, I can say, tertiary one, so it doesn't react with benzene sulfonyl chloride at all, and that is why there is no reaction in it. Okay, now moving to the electrophilic substitution reaction. So the first one, if you take aniline and treat it with HNO3, that is okay, first let's talk about halogenation. So if you treat it with bromine and water, so it will give you like all 2,4,6 tribromoaniline is produced. You will not get single product here. And always remember, NH2 is an electron donating group, so it is orthopara directing. Okay, now when you treat it with nitric acid, okay, concentrated HNO3 and H2SO4, so what we get is, because it is electron donating group, right, we expect that we will get mostly what, ortho and para products, but here there is something which is very different, that you get para product you get ortho product, but you get meta product in such a huge amount. Okay, the reason for the meta product to be formed in such a large amount is the protonation of the NH2 in the acidic medium, and then it behaves as a deactivating group. So that is the second reaction, nitration. Now when you treat it with sulfuric acid, so here you get like a salt of the compound. Now the thing is, how I can get only one product of bromine, one product of nitration? So for that we have to reduce the reactivity of this NH2 group, and to reduce the reactivity of NH2 group you have to treat it with anhydrides, and when you treat it with anhydrides you get NHCOCH3, which is an acetanilide. Okay, now into this one, if you treat it with nitric concentrated HNO3 and concentrated H2SO4, you will get only the para product. Now to get back our NH2, you have to do hydrolysis, and you will get NO2, and your NH2 is also there. This NHCOCH3 gets converted to NH2. Now similarly to this NHCOCH3, if you treat it with bromine and acetic acid, you will get bromine at the para position, and then when you treat it with OH minus and H, this one, so you will get para bromoaniline. Okay, so bromine will be produced at the para position. So just let me write on with a different color here. So bromine will be produced at the para position to give you para bromoaniline. Okay, now we have benzene disonium chloride preparation. So we have C6H5NH2 with NaNO2 and HCl. It will give you C6H5N2 plus and Cl minus plus NaCl plus water. Now the physical properties here is like colorless and its solubility. Now if I talk about the chemical reactions of benzene disonium chloride, the first one we will see those reactions where there is a displacement of the N2 group. Means you have this group, right? You have here N2 plus and Cl minus. So this N2 plus is replaced by which reactions, that we will see. So first I can replace with Cl minus and Cn minus, then I have replacement by I minus, replacement by F minus, replacement by H, replacement by OH, and replacement by NO2 group. Okay, so first let's see, if you have this benzene disonium chloride and if you want to replace with Cl minus or Cu minus, you can use copper salt. Okay, Cu2Cl2 or HCl, Cu2Br2 or HBr, CuCN or KCN. Now all these reactions comes under Sandmeyer reaction. Now that will give you ArCl, ArBr and ArCN. Now you can treat it with CuHCl, just copper powder, not the salts of copper, or copper HBr, that is called as your Gattermann reaction. So with that also you can get ArCl and ArBr. Now after that you can treat it with Ki to give you ARI. So we have understood how I can get Cl minus, Br minus, Cn minus and I minus. Now for F minus, first of all you need to treat it with HbF4. So this is H plus and this is BF4 minus. So what will happen? N2 plus will be there, and with that BF4 minus will combine. After that when you heat it, you will get simple fluorobenzene plus N2 plus BF3. Now if I treat it with this one to replace with hydrogen, means you just want their hydrogen to come. Okay, hydrogen to come, so you can treat it with H3PO2 water or ETOH. In both the case you will replace this N2 group with H. Now to replace it with OH, means to get phenol, you have to treat it with water. Okay, now to get here NO2 group, first we'll treat it with HbF4, so we'll have N2 plus and BF4 minus. After that we will have NaNO2 and Cu, and that will give you NO2 group. Okay, so that is why how benzene disonium chloride reactions are there. These are very very important. And next one is a set of coupling reactions that we have. So if you treat benzene disonium chloride with phenol, so here there will be coupling reaction to give you para-hydroxyazobenzene, which is a orange dye, and if you take benzene disonium chloride with this one, then you will get para-aminoazobenzene. Okay, yellow color dye. Now coming to the uses here, adrenaline contains a secondary amino group and it is used to increase the blood pressure. Ephedrine is a secondary amino group and it is also used to increase the blood pressure. Now Novacin is a synthetic amino acid. It is used as an anesthetic in dentistry, and Benadryl contains a tertiary amino group and used as an antihistaminic drug. Okay. Now these are all about the chapter amines. Now let's move to the last chapter of our organic chemistry, that is biomolecules, which has a weightage of 9 marks. Okay, so here first we will study about carbohydrates, then proteins, then enzymes, vitamins, nucleic acids, and lastly about hormones. So carbohydrates are defined as optically active polyhydroxyaldehydes or ketones, which can produce such units on hydrolysis. So if I talk about the classification of carbohydrates, the first category is the product of hydrolysis and the second one is the reducing nature. Now product of hydrolysis, we have monosaccharides, oligosaccharides and polysaccharides. Means when you have bigger compound, and when you break it, okay, so what do you mean by monosaccharides? These are those units which cannot be hydrolyzed further. Now oligosaccharides means if you break these big compounds, you get monosaccharides in the number of 8 is to like 8 to 10 monosaccharides. If you get, then we call it oligosaccharides. Now if you break polysaccharides and you get more than 10 monosaccharides, then we call it as polysaccharides. Now based on the reducing nature, we have reducing sugars and non-reducing sugars. Okay, reducing sugars are those which will reduce the tolerance reagent and Felling's reagent, and non-reducing sugars are those which reduce the tolerance reagent and Felling's reagent. Now we will talk about the preparation of glucose here. So the first one is from starch. So if you take starch and then you hydrolyze it, you will get n number of glucose molecules. And the second one is the hydrolysis of, this one is the starch one. And if you take sucrose and you hydrolyze it, you will get glucose and fructose. Okay, this is how we can produce glucose. Now talking about the structure of glucose, see, the scientists just knew the formula of the glucose, but then there were a lot of experiments done to prove the structure of glucose. And the formula of the glucose, we all know, it is C6H12O6. Okay, so the first reaction was done with Hi. So when you reacted with Hi, we get the product N-hexane, and this gave us a conclusion that all the carbons in the glucose are in a straight chain. Now the second reaction we did was NH2OH and HCN. So when we reacted with NH2OH, you got imine, and when you reacted with HCN, you got cyanohydrate. Now these two reactions prove the presence of a carbonyl group. Now when you react it with bromine water, so the CHO group gets converted to COOH group. Now the carbonyl group is present at an as an aldehyde group, that is confirmed. Now when you treat it with any anhydride, so we got penta-acetate derivative, so that shows the presence of 5 OH groups. Okay, now out of the 5 OH group should be attached to different carbon atoms. Now when you have reaction with HNO3, so when you react this particular CHO group, okay, and you have COOH group, and also when you treat it with this one with a strong oxidizing agent, you get another compound, that is saccharic acid and gluconic acid. Now this shows that this OH group 1 which is present is a primary group. Okay, I'll just repeat here what I'm saying. Please understand that. See, concentrated nitric acid is a strong oxidizing agent. Okay, and strong oxidizing agent can convert primary alcohols to acids. Okay, and we have already seen that CHO group is already present in our compound, and aldehydes can easily convert to acids with an oxidizing agent. Okay, so now when I use a strong oxidizing agent, so the glucose molecule gave me saccharic acid, even the gluconic acid gave me saccharic acid, means here both the groups are converted to acid groups. So that one COH group we are getting because of CHO, there's no doubt in that, but the other COH group which we got is due to the oxidation of a primary OH group. So that confirms that out of the 5 OH groups, one OH group is primary. Now based on that, the structure of the structure of glucose is shown to you. Okay, now this is the open chain structure of glucose, and there are certain limitations to this open chain structure of glucose, like it does not react with Skiff reagent. The pentaacetate of this form do not contain a free aldehyde group. It exists in two forms, that is alpha and beta. So these three observations were not explained by the open chain structure of glucose. So that is why scientists suggested that there is another structure of glucose also exists. And how is that structure derived? So that structure is derived when the OH, the group last OH reacts with the carbonyl group, and we get two structures here like this called as Howard structure. Okay, now in this Howard structure we have two, I can say, anomers. One is your alpha and one is your beta. So if the OH group is towards the down, then we call it alpha, and when the OH group is towards the top, we call it beta. Okay, now here one more thing I just want to mention, that if this OH group is on the right hand side, then you denote it with capital D. Okay, D. Capital D is denoted because of this OH group which is on the right hand side. Okay, now the plus symbol, what does it denote? It denotes that it is dextrorotatory, means it rotates the plane polarized light in clockwise direction. Now we have this word called pyranose. Okay, the pyranose is influenced from this word pyran. You can see the structure here, there's a heteroatom oxygen, and in the glucose structure also there's a heteroatom oxygen. So because of its similarity, it is considered, or it is named as pyranose. Now, if you see the structure of fructose, so fructose is a ketose group. It has 6 carbon, but it has a ketone functional group, and it can also exist in the alpha and beta form. But here if you see, it is minus here. That means fructose is levorotatory, and capital D denotes that this OH group is on the right hand side. Okay, now beta here because the OH group is present at the top, and alpha here because this OH group is present at the bottom. Now here also furanose is derived from this word furan, which is having a structure similar to that of the fructose. Now we'll talk about the disaccharides. The first disaccharide we have is sucrose. Sucrose is made up of D plus glucose and D minus fructose. When it dissociates, it gives you D plus glucose and D minus fructose. And there is a linkage between C1 of alpha D glucose and C2 of beta D fructose. Okay, so it is a non-reducing sugar, and this structure is very, very important, and it has been asked in many times in the exam. Now inversion, so what happens is sucrose is actually dextrorotatory, but when you leave it for some time for hydrolysis, it breaks to give you glucose and fructose. Now glucose is dextrorotatory, but fructose is levorotatory by a minus 92.4 degree. So the overall rotation of the sample becomes levorotatory. Okay, so the hydrolysis of sucrose brings about a change in the sign of rotation from dextro to levo, and this product is called as invert sugar. Now we have disaccharides, that is maltose. Maltose is made up of beta D sorry, one second. Okay, so this is a slight error here. So this one is composed of alpha D glucose. Okay, so our maltose is made up of 2 units of alpha D glucose, and there's a connection between C1 of alpha D glucose to C4 of alpha D glucose. Okay, please remember this one is C1 to C4 of alpha D glucose, and it is a reducing sugar. Now in lactose we have beta D galactose and alpha D glucose, and here there is a connection between C1 of galactose and C4 of glucose. And this diagram is also important, and this maltose structure diagram is also important. Now, if I talk about polysaccharides, so polysaccharide means when you break these compounds, you get n number of monosaccharides. So the first polysaccharide we have is starch, and it is made up of alpha glucose units, and is in two forms. One is your amylose and another one is amylopectin. So amylose is water soluble, whereas amylopectin is water insoluble. Here we have 15 to 20% of starch, and here we have 80 to 85% of the starch. This is an unbranched chain, and this is a branch chain. Now here the alpha D glucose units have C1 C4 linkage. Here they have C1 C4 linkage as well as C1 C6 glycosidic linkage. Now coming to amylose and amylopectin, the structure is not important from exam point of view, but you need to understand. In amylose we have a straight chain structure, whereas in amylopectin you have branch structure. Now I'll be summarizing whatever connections we have studied in disaccharides and polysaccharides. So in disaccharides, the sucrose monomer units are alpha D glucose and beta D fructose, and there is C1 to C2 linkage. Okay. Now in maltose, the monomer unit is alpha D glucose, and here you have C1 of one glucose to C4 of another. Now lactose is made up of beta D glucose and beta D galactose. So here it is C1 of beta D galactose to C4 of glucose. Now in starch, so here I think there's a small correction. You can see, yeah, beta D galactose and beta D glucose is there. So I have C1 of galactose and C4 of glucose. Now starch is made up of alpha D glucose. It has amylose and amylopectin. Now we will just see cellulose and glycogen. Then I will cover that too also in detail. In cellulose, the monosaccharide units is beta D glucose, and here the connection is between C1 and C4. Now in glycogen, it is alpha D glucose. Here also the connection is C1 to C4 and also C1 and C6. So the glycogen structure is very similar to amylopectin, but it is more branched. So if you see cellulose structure here, so here we have beta D glucose unit, C1 C4 connection, and they are found in the cell wall of the plants. In glycogen, the carbohydrates are stored in the form of glycogen. So it is basically animal starch present in liver, muscles, and brain, also found in yeast and fungi. Next, we'll go to the next biomolecules, that is proteins. So proteins are, you can say, polymers of amino acids, and the structure of amino acids looks like this. You have one carbon, one side there's an acidic group, and one side there's a basic group. Okay, and there is one R group. Now based on this R group, we can have total of 20 amino acids. So how are these amino acids classified? Let's see that. So the classification of amino acids is first on the basis of their nature, means acidic, basic, and neutral. So acidic amino acids means if you have more than one COOH group, basic amino acids means if you have more than one NH2 group, and neutral means if you have one amino and one COOH group. Now on the basis of synthesis, we have essential and non-essential amino acids. So essential are those which cannot be synthesized in the body. Okay, cannot be synthesized in body. It has to be consumed from the diet. Whereas non-essential amino acids are those which can be synthesized in the body and doesn't has to be taken from the diet. Now these are the list of your essential amino acids. Every year question is asked from here, so please remember the definition as well as the example. Now let's move how the two amino acids are connected with each other. So there's a linkage called as peptide linkage. Okay, so if you see here, OH bond breaks from here and H bond comes here, and there's a loss of water molecule to give you CONH, that is your peptide linkage. And you can see that this is a here we have, first of all, this is glycine and this is alanine. So we have glycine and alanine mixture, GLY and ALA. Now when the number of such amino acids is more than 10, then we call it as polypeptides. And if a polypeptide is having a weighing more than 100 amino acids and 10,000 atomic units, then we call it as a protein. Now if you see the structure of proteins, basically we can divide it first on the basis of shape, that is fibrous and globular protein, and on the basis of structure we have primary, secondary, tertiary and quaternary proteins. Okay, so first if I talk about molecular shape, so fibrous proteins are those which run parallel to each other and are held together by hydrogen and disulfide bonds, whereas globular proteins are those which coil around and are in a spherical shape. Fibrous proteins are insoluble, whereas globular proteins are soluble. Example here, keratin, you have myosin, here we have insulin and albumin. Now we have the structure of protein is leveled in four types: primary, secondary, tertiary and quaternary. So in primary structure, it is just the sequence of amino acids. Okay. Now in secondary structure, what happens? These sequence of amino acids undergo further folding. Okay, so if they coil around, just they undergo coiling, and then they are held together by the hydrogen bonding. They are stabilized by hydrogen bonding and they're coiled around. This is called as alpha helix structure. But in beta pleated sheet, the polypeptide chains run parallel to each other and are held together by intermolecular hydrogen bonds. You can see here that this hydrogen bond which is present, this is there in the coiling of a polypeptide chain. And here you can see they are running side to each other and there is intermolecular hydrogen bonding. Now comes the tertiary structure. In tertiary structure, there's overall folding of the secondary structure, and they exist in two major shapes, that is fibrous and globular. And the tertiary structure are stabilized by hydrogen bonds, disulfide linkages, van der Waals and electrostatic force of attraction. Now when you have quaternary structure, okay, the further folding of the tertiary structure gives you quaternary structure. Example here is your hemoglobin. Now, when you have primary structure, it is just the sequence of amino acids. The secondary amino acids of the secondary structure is the alpha helix or the beta pleated sheets. The tertiary structure is fibrous or globular, and the quaternary structure is the 3D arrangement of these structures. Now we'll talk about protein denaturation. So native protein with unique 3D structure and biological activity, that is called as native protein. But when you disturb this conditions of like temperature or pH, then the protein starts to uncoil. Okay, and that uncoiling of protein is called as denaturation, where they lose their biological activity. Example is coagulation of egg white and curding of milk. Next, we'll talk about enzymes. So enzymes are nothing but biocatalysts. They are generally globular proteins and they are very specific in nature and speed up the reactions by decreasing the activation energy. Now the most important, we'll go for vitamins. These are very like important compounds but are required in small amounts to function specific biological functions and in the normal maintenance of the organism. Now vitamins are classified as fat soluble and water soluble. Fat soluble are those which are soluble in fat and oil. Okay, and they have example is A, D, E and K, and they can be stored in liver and tissue. Now, in case of water soluble, these are soluble in water. Example is B and C, and they are should be taken regularly in our diet because they are soluble. They are easily excreted from our body through urination or sweating. So that is why you need to consume vitamin B and C sufficiently from your diet. Now, here there is an exception. Vitamin B12 is again a fat soluble vitamin. Now we'll be talking, this table is very important and I just want all of you to remember this table. You should be knowing the vitamins, its sources and its deficiency diseases. Okay, and for vitamin B especially, you should know its chemical name as well. For example, B1 is thiamine, B2 is riboflavin, B6 is pyridoxine, and vitamin B12, vitamin C is your ascorbic acid. So whichever chemical names are written, that you should be remembering with their deficiency disease and the sources of that vitamin. Next, we'll move to nucleic acids. So nucleic acids are of two types in our body. One is RNA and DNA. So RNA is called as uh, I can write deoxyribonucleic acid. Okay, and DNA is called as deoxyribonucleic acid. Okay, deoxyribonucleic acid. Now we will understand this in detail. See, so nucleic acids, like you have seen that the carbohydrates are the polymers of monosaccharides. Proteins are the polymers of amino acids. Similarly, nucleic acids are the polymers of nucleotide. And each nucleotide contains three components. So, what are the components of a nucleotide? You have one pentose sugar, a phosphoric acid, and a nitrogen-containing base. Okay. Now, the pentose sugar present in DNA is beta D ribose, and the pentose sugar present in RNA is here it is RNA. The pentose sugar present in RNA is beta D ribose, and the pentose sugar present in DNA is beta D 2 deoxyribose. Okay, so this is DNA. Clear? Now we will talk about how these nucleic acids are made, or how this nucleotide is made. So first of all, you see in a nucleotide there is a sugar, there is a nitrogenous base, and there is a phosphoric acid. So on the first position the nitrogenous base is attached, and on the fifth carbon there is a phosphate group is attached. Okay, so the phosphate group you can see is attached on the fifth carbon. Okay, so this is the entire structure is what? This entire structure is nucleotide. Now, when you have the sugar and only the base is attached, okay, at the first position, then that particular structure is called as nucleoside. Okay, nucleoside and nucleotide. Now what we have, how these two nucleotides are connected with each other. So you can see this is one nucleotide where on the first carbon you have base and on the fifth carbon you have phosphate group, and this is the second nucleotide where on the first carbon you have base and on the fifth carbon you have phosphate group. Now these two are connected by 3' to 5' connection, means 1, 2 and 3. Okay, so this 3 group and 5 group, there is a connection between this 3' of one nucleotide and 5' of another nucleotide to form a bond called as phosphodiester linkage. So you can see I have sugar base phosphate group, then I have sugar base phosphate group. So this connection is going on, and this whole chain makes your nucleic acids. Okay, so we understood that the sugar that is present in DNA is deoxyribose sugar, whereas the sugar used in RNA is your ribose sugar. Okay, now there's one more difference which I can say in the nitrogenous bases here. Okay, so what are the nitrogenous bases that is used in DNA? It has adenine, guanine, thymine and cytosine, whereas in RNA the nitrogenous bases are A, G. Instead of thymine we have uracil and cytosine. Okay, that is the difference in the nitrogenous base, and we have also seen the difference in the sugar. So in RNA we have beta D ribose, whereas in DNA we have beta D 2 deoxyribose. Okay, so now we have understood this also. Now, what is the structure of this nucleic acid? So, in DNA, two nucleic acids coil around each other and are held together by hydrogen bonds, and the two strands are complementary to each other. So, always remember, adenine forms bond with thymine and guanine forms bond with cytosine. So, if you know the sequence of the nucleotides in one particular nucleic acid, you can definitely predict for the other. So, for example, there is one nucleic acid like this where the nitrogenous bases are present like C, G, G, A, T, A, T. Okay, then what will be the one which is the complementary, means the other strand which is present, what will be its sequence? So that we can easily predict like this, because we know that A will bind with T and G will bind with C. So here if it is C, it has to be G, again G, then C, again G, then C, then you have A, means here it will be T, T means A, and A means T, and again T means A. Okay, now it helps to store the genetic information and is responsible for protein synthesis. Now we will talk about hormones. So hormones are our intracellular messengers, and they are secreted by endocrine glands directly into the bloodstream. So hormones are classified into three important categories. The first one is polypeptide. Here we will study about insulin, endomorphins and glucagons. Next, we have amino acid derivatives. Here we will be studying about epinephrine, norepinephrine and thyroxine. And the third one is steroids, where you have estrogens and androgens. So first let's talk about polypeptides. Okay, so under polypeptides what we have, insulin, endomorphins, and glucagons. Okay, so first let's see the function of glucagon here. So these two I'll just write. These two are from the category of polypeptides. Okay, so glucagon is used to increase the blood sugar level, whereas insulin reduces the blood sugar level. So these two together work to maintain the sugar level in the blood. Next, we will talk about the amino acid derivatives. Okay, amino acid derivatives. So epinephrine and norepinephrine, these two are used for the responses to external stimuli. And then we have thyroxine. This is produced in thyroid gland, and it is an iodinated derivative of amino acid thyroxine. Here low concentration causes hypothyroidism, lethargy and all, and high concentration causes hyperthyroidism, that is enlargement of the thyroid gland. Now this one, that is epinephrine and norepinephrine and thyroxine, these are what? Amino acid derivatives. Now we'll talk about the steroid hormones. Now steroid hormones can be synthesized by two organs. One is your adrenal cortex, another is gonads. So the one which is secreted by adrenal cortex, we have glucocorticoids and mineral corticoids. Okay, so these are released by adrenal cortex. They help in carbohydrate metabolism, modulate the inflammatory reactions, and are involved in reactions to stress. And mineral corticoids control the level of excretion of water and salt by the kidney. Now there's a deficiency disease called addition disease, which is caused when the malfunctioning of adrenal cortex takes place. And the symptoms here we have is hypoglycemia, weakness, and increased susceptibility to stress. Now the steroid hormones are also released by gonads. Okay, so the example here is testosterone, which is your major male hormone and responsible for the secondary characteristics in male, like deep voice, facial hair, and physical constitution. Similarly, we have estradiol, which is a female hormone and is responsible for development of secondary female characteristics and participates in the menstrual cycle. And similarly, progesterone is also a hormone which is responsible for preparing the uterus for implantation of the fertilized eggs. Okay, so children, this is all about the hormones. So we have completed the whole revision of organic chemistry, and here's something very very important. KCT 2026 examination is very close, and if you really want to ace this examination with the top rank and want to secure a seat in the top colleges of Karnataka, then only studying will not help you. You need to practice test, you need to analyze, and you need to improve, and for that you need a perfect test series. So to help you with this, I have launched the Fighter KCT 2026 test series, which is designed by KCT experts and is based on KCT exam pattern and syllabus. Okay, here you will get detailed solutions, video solutions for chemistry, and the most important thing, a detailed analysis report after every test, which will help you to analyze your strength and weak areas. And all these things are available at a very very affordable price of just rupees 399. So if you really want to boost your preparation, this test series should be there in your, I can say, resource list. So the link is there in the description section. So click on the link and purchase right now, as the prices may go higher later.